Good afternoon. Thank you for the intro. My name is Imtiaz. I am going to talk about our work on Bluetooth non-compliance checking. This is a joint work between Purdue and Penn State. So let's get to it. So Bluetooth Low Energy, or BLE, is the most widely used low energy communication protocol, with BLE devices expected to exceed 7 billion by 2026. BLE has a wide range of use cases involving audio streaming, data transfer, location services, and creating device networks. With the recent COVID-19 pandemic, BLE has been widely adopted and used for a lot of COVID-19 based contact tracing applications. This shows the importance and impact of this protocol. So on a high level, all the previous works on Bluetooth Low Energy Protocol implementations can be grouped into 4 categories. First one is different manual analysis for bug finding. Second is different testing approaches. Third is formal verification of protocol spec. And last one is based on rehosting and reverse engineering. Though all these works have shown real promise, one important research vector is still missing, that is non-compliance checking based on the specification. So that is what we want to talk about. So with such an important protocol like Bluetooth, it is expected that the implementations follow the specifications. Failure to follow the specifications can create non-compliance that can either lead to exploitable attacks, such as denial of service, or more seriously, security bypass, and also interoperability issues where multiple devices fail to properly communicate with each other. So the main goal of our work is to design an automated non-compliance checking framework for BLE implementations. So that is I'm going to talk about in future slides. So what are the challenges of designing such an automated non-compliance checker? The first one is BLE doesn't have, or Bluetooth doesn't have any formal specification. So it's not possible to directly check non-compliance from an implementation point of view. Second, there is no formal implementation that developers can use and follow. Third, BLE is a really complex protocol with thousands of pages of spec, different layers, different association methods. So it creates scalability while designing such a framework. And last one is BLE is a human-in-the-loop protocol. That means like there is human behavior involved. We had to look for passkey entry or pairing code to properly follow the protocol. That creates a lot of challenge when we want to create an automated non-compliance checking framework. So to resolve all these challenges, we designed BLEDiff. The critical idea for BLEDiff is that if 2 devices behave differently from each other, that means at least one of them is non-compliant from the specifications. So based on this idea, we kind of utilize a lot of different devices, and based on differential testing and scalable active automata learning, we find deviating traces. So these traces are basically where for the same input, 2 devices behave differently. And through this, we avoid the challenge of requirement of formal specification and also the requirement of formal implementation. So on a high level, for this non-compliance checking, we need to solve 2 major issues. First is we need to come up with a formal model from the protocol implementations. And secondly, we need to compare the models, the different models of BLE to find non-compliant traces. So following this discussion, BLEDiff has basically 2 modules, one for finite state machine learning, and second is for checking these finite state machines. So for this finite state machine learning, one possible idea can be to do reverse engineering. However, reverse engineering requires heavy domain expertise, and that cannot be easily generalized to a lot of devices. So we extract finite state machine using a black box learning approach, which is called active automata learning, which I will discuss later on. So once this model or finite state machines are extracted, we compare them to find diverse deviating behaviors. So these are the future for the talk. I will talk about these 2 modules, our findings, and lastly a summary. So going to active automata learning, so the underlying technique that we use for finite state machine inference is based on active automata learning. In this approach, a learner sends a sequence of queries to the system under learning. The system responds with outputs. With this input-output behavior, the learner infers a finite state machine of the protocol implementation. So though, like in practice, it's really easy, for real-world systems like Bluetooth, we need to design a mapper that kind of converts these abstract symbols to concrete BLE packets, and similarly do the opposite side, convert real output packets to abstract packets so that learner can learn finite state machines. So now about some challenges. So the technique is fairly simple, but there are multiple challenges in applying active automata learning for a complex protocol like Bluetooth. One of the major challenges that I talk about is scalability. So for Bluetooth has a lot of different modules, different association modes that I already talked about. So in case we want to learn the finite state machine for all these protocols, sub-protocols, and modules with all the symbols, the scalability of the learning explodes. In previous work, it has been shown that the learning takes around 10 days, but in Bluetooth, with this enlarged scope and complexity, it will take much more. So here we need to come up with an approach to resolve this fundamental challenge. And we devise a new active automata learning based on divide and conquer. So at the core of the idea is that we divide the Bluetooth protocol into multiple sub-protocols. We identify dependencies for each sub-protocols, their initial states, input symbols, and extract finite state machine for each of them. These finite state machines are later sequentially merged to create the whole finite state machine of the protocol. So our FSM inference module actually talks to each of the layers as sub-protocols, get finite state machines from all of them, and then these finite state machines are combined together sequentially to create the large finite state machine of the total BLE protocol that we utilize for next steps. The second challenge I'm going to talk about is standard compliant non-determinism. So as I discussed earlier, we need a mapper that will do the mapping between abstract symbols and concrete BLE packets. But for BLE, the things are a bit different because BLE has two major issues. First of all, in BLE, a packet can be triggered by both central and peripheral. And also, some of the packets do not have a specific ordering, mostly linked layer packets. So the issue is, if we generate a query, instead of getting a response, the system can generate its own query. So designing sort of like a differential analysis-based framework, this can create false positives, and that will be a big issue for our framework. To resolve that, we design our mapper differently from all the previous approaches. The idea is the learner sends a query, but in case the peripheral generates its own query, the learner drops the packet and internally responds with a response. This is important, otherwise the protocol flow will stuck and we will not be able to communicate. Eventually, the system responds with the response packet and we forward it through. So with this design, we make sure that we don't have false positives in our system and we can systematically learn for all the devices. The last part I'm going to talk about is human interaction and BLE addressing. So we all know that BLE has some privacy issues. So BLE addresses are changed automatically after a certain time. This creates an issue when we are trying to design an automated system. So we design a very simple approach. We first turn off the device, do a probe, what are the devices, then we turn on the device, and doing a diff, we figure out what is the device that we are trying to test. The last part for handling human interaction, we do the tedious task of engineering a lot of key press simulations so that we can automatically test all those systems. Now we got the finite state machines from the learning module. The second task would be to find diverse deviating behaviors. So for this, we convert the equivalence checking problem into a model checking problem with a safety property that if for two different outputs, we get the same, for two different outputs, if we get the same input, that means like for the same input, we are getting a deviating behavior. So if we learn this property once more, then it's high probability that we will get the same deviating behavior, which we don't want because we want to find a lot of diverse deviating behaviors. So I will show that with a simple example. So here there are two finite state machines. There are two deviations from A to B and B to C. So if we run our property, we will get the first deviation from A to B. The previous works, they kind of removed this transition so that this same deviation is not generated again. But as you can see, this creates a problem because the finite state machine soon becomes like disjoint, and it is not possible to detect long diverse deviating behaviors. So we call this elimination-based model modification. To resolve this, we kind of take a different approach. Instead of removing the transition, we modify the output so that this same deviation is not generated again. We get a different deviation for like B to C if we run the property again. We call this refinement-based model modification. We show in the paper a lot of evaluations on how this improves the capability of finding diverse deviations. Now, from findings point of view, we tested BLEDiff on 25 devices. We found 13 unique non-compliant behaviors, 9 high-severity CVEs, and lastly, we got bug bounties acknowledgments from all these vendors. So there are a lot of interesting bugs. I will just talk about one for time's sake. So in BLE, there are different association modes. The most important one is passkey entry, where basically the user sees a passkey and input in the device. So going on to the protocol flow, for the device, it should show like a prompt like this, and the assumption is the user will input the keys. But what we figured out that the user don't need to input anything. In some devices, if the key is assumed to be 0 and the packet is sent, it basically falls through and pairing and bonding is done. So as you can see, it's like really serious. So the good thing is it's already been updated, so update your phones. Hopefully that will be resolved. So yeah, lastly, summary, we designed an automated black box non-compliance checker for BLE called BLEDiff. We devised a new approach on active automata learning that is based on divide and conquer. We found 10 new attacks and 2 interoperability issues. So BLEDiff is completely open sourced. Please try out our code, our tool. It should be interesting. And for more information, you can visit the website. Thank you.
Questions? Let me ask one question. So how can we use that tool for other protocols? For example, Wi-Fi or LoRa, those kind of other wireless protocols?
Yeah, that is a really interesting question. So basically, as I showed in the slides, the first thing we need to do is design a mapper so that the communication between the abstract symbols is converted to the protocol that we want to test. So in case of Wi-Fi, we need to design a mapper that can do this mapping. And also, we need to like figure out what are the input and output symbols for that protocol.
Thanks. Yep. Go ahead.
So you mentioned at some point of time that you used some model checking techniques. Right?
Yeah.
And I was wondering if you can elaborate a little bit more on what specific model checker you used.
So we used NuXMV for this task.
Okay.
So
for NuXMV, there are a number of limitations, like you cannot incorporate real numbers and so on. So can you explain a little bit about the limitations that one can extend in the future work related to that?
Yeah, sure. So basically, the finite state machines we get from the active automata learning doesn't involve anything that is a limitation for NuXMV. So we just convert the equivalence checking problem to a model checking problem and use NuXMV for our task. So for this kind of equivalence checking, NuXMV should work fine. So we are kind of following the protocol finite state machine that we got from our previous step and using that to do the non-compliance checking for the next step.
Right. So the basic assumption is that equivalence checking to model checking reduction, that's the basic assumption.
Yeah.
The tool works fine.
Yeah.
Okay. Thank you very much.
Right. Let's thank the speaker.